Okay, so in this lecture, we're going to talk about PID control. PID control stands for proportional integral derivative control. It's actually a three-term controller, and if you look at the structure here, this is our typical unity feedback control structure. The PID controller is essentially everything in this dotted blue block, right? That is the actual controller we're talking about today. And the actual form for the transfer function of that controller is given here. The PID controller is actually worthwhile to study because it's probably one of the most widely used control schemes in all of industry. And this is due to, as we're going to find later, essentially its robustness and its ease of implementation. Okay, so it's very simple to implement a basic PID control scheme. And what we're going to find later is that it also addresses the issue of whether or not you have a model for the plant. Okay, so we're going to do a bit of analysis um, based on having a known plant model, and so we're going to look at some of the inner workings of the PID controller, but we're also going to address the situation, which happens a lot in practice, where you don't know what the plant model is necessarily, and you're not willing to spend the time to identify that system. Okay, so the PID controller is very uh, applicable in those scenarios where you don't have the plant model, because there are a lot of algorithms that are available that you can use to tune a PID controller um, without without knowledge of the plant itself. As I mentioned before, the PID controller itself is outlined here. The controller itself is always a transfer function from the error signal to the control command. And in this case, you can see that the error is immediately split off into three different directions. Essentially, all of the error goes through each and every one of these three control blocks, and the outputs of each of those blocks are eventually summed together to get the overall control command. Okay, so that's the sort of how this controller works from the block diagram standpoint. What we're going to do is learn how essentially each one of these control gains serves to influence the closed loop output. Okay, it's real important to understand that first of all, in the past we've been dealing with controllers like this, which is just a simple gain controller. Um, in the previous lecture, lecture 7, we actually talked about a controller that looks like this, K over S. And the reason for doing this was to try to bump up the system type for that particular system and therefore be able to track different types of references. Okay, so this controller, the PID controller, actually contains both of those, right? There's a proportional gain just by itself. There's an integral gain, which is the Ki over S. And there's also a third term called a derivative term, which is Kd times S. And each of those different gains serves to influence a response in a different way. And that's what we're going to focus on for the first half of this lecture. Is exactly how do those three different gains influence the output. Now, having said that, well, it should be noted that this is a first scenario when we're running into a controller that has multiple gains. Okay, so there's three different essentially control knobs that you can play around with to alter the output, um, which is kind of a double-edged sword, right? It gives you a huge design space. It allows you to place the closed loop poles virtually anywhere in the S-plane, but at the same time, that's potentially a problem. Like you have too many options, then it becomes a matter of understanding the inner workings of each one of those gains in order to settle on a set of gains that works for your applications. Okay, so what I'm trying to say is you have a ton of design space with the three control knobs, but if you don't know what you're doing and you're just kind of messing around and seeing what types of responses you get, you may never settle on an appropriate response. Okay, so what we're going to do is sort of hone in on those three gains and learn how they each impact the closed loop response. Okay, so generally speaking, okay, so just from a very high level, the first thing we're going to do is sort of define the overall effect of what the three gains purpose are, and then we'll try and dig down a little bit deeper to see why that's the case. Okay, so generally speaking, the proportional gain. So if you crank up the KP gain in your control system, you are typically going to see a faster response. That should be no surprise because if you think about what the KP gain is doing, it's literally taking in the error signal and scaling that error by a constant value and spitting out a control command. Okay, so if the KP is larger, even if your error is small, you're going to get a large control command, which would contribute to a faster response on the system behavior. Perhaps less obvious is what the integral gain does. So the integral gain is going to improve the steady state performance. Better steady state performance. This can be quantified in a number of different ways, but actually we have already seen the effect of the integral gain on the steady state response. If you think back to the previous lecture, lecture number 7, we said that, well, if you incorporate an integral control scheme, which is having basically placing a pole at the origin, so the control scheme looks like Ki over S, what you are doing is effectively bumping up the system type by one level. And if you bump up the system type, the higher the system type of your system, the more complex types of references you are able to track perfectly with zero steady state error. So that's how, generally speaking, if you increase the integral gain, you're going to improve that steady state output. The derivative term, we haven't seen this form of a controller yet, but the derivative term serves to improve the speed of convergence. So you generally get a smoother response with derivative control, and you also get faster convergence. Okay, so these are basically your three high-level effects of what those gains serve to do in the output. There's often a question of, well, what's the difference between fast response and fast convergence? Well, I can show you. A response that, an output that responds quickly just means that stuff happens right away. So if you're starting at 0, a system with a fast response may immediately shoot up to some large value, right? And it may overshoot the final value by a little bit, and then it may sort of oscillate as we've seen in the past, something like that, right? So this is very fast response, right? This is fast response. It responds very quickly, yet it takes a long time to converge to its final value, right? So perhaps there's very little damping in this system, and so it actually takes a long time to converge to its final value. On the flip side, a response that converges quickly, well, stuff may not happen right away, right? It might sort of take its time getting going, but perhaps this controller is designed so that once it does get going, it basically settles at the final value very quickly. Okay, so this is a scenario where we have fast convergence, but not necessarily fast response. Okay, so there's minor differences, but they're actually pretty big differences, but they're subtle. Okay, so that's the difference between fast response and fast convergence, and ultimately the difference between the proportional gain and the derivative gain. Okay. Okay. So this is sort of like a high level overview. Knowing that this is the general effect of all three of those gains can definitely help you when you're tuning your PID control. But it does help to understand why these, essentially why does a proportional gain give you faster response, and why does derivative gain give you a faster convergence and smoother response. Okay, so what we're going to do now is just sort of dive one level deeper and sort of figure out why that's the case. And to do so, we're going to take a pretty quintessential example. We're going to look at our mass spring damper system. So going back to something that feels hopefully very familiar. we've got a mass spring damper system. There's a damper coefficient C, spring constant K, mass of M, displacement of Y, and a forcing function of U. Okay, so there's some type of external force being applied to that system. And what we already know is that the transfer function from the input force U to the output displacement Y, we already know the form of this transfer function because we modeled it several times in the past. It looks like 1 over ms squared plus cs plus k. The only thing we're going to do differently here is we're going to kind of approach this from a different perspective. Okay, so one thing we haven't done is to try and identify if sort of the kind of like the names of these terms. Okay, so the mass spring damper system is a very literal example in this case because this C term, the middle term, is called the damping term, right? For any second order transfer function, whether or not it's a mass spring damper system, any system that exhibits second order behavior like this one, the middle term is called the damping term. Okay, so even if there's not a physical damper in the system, the middle term, whatever C the coefficient is called the damping term. Like I said, in the case of the mass spring damper system, it's very literal because the damping term is actually the damping coefficient for that damper that's in that system. The s to the 0 term, this sort of coefficient on the end, this is called the stiffness term. And again, in this case, it's very literal. The stiffness term is literally the spring constant of the actual physical spring on that system, right? But we have seen other second order systems in the past that exhibit second order behavior. For example, a pendulum, right? A pendulum has essentially the same transfer function as a mass spring damper system, but there's no spring on this system, and there's no physical damper on this system, right? The spring, essentially, the restoring force comes from gravity, and the damping force is due to aerodynamic drag, okay? So whatever you get for the middle term is always called the damping term. Whatever you get for the stiffness, whatever you get for the K value here is a stiffness term, whether or not there's a physical damper or spring in the system, if that makes sense, okay? Nonetheless, what we're going to do is sort of analyze this type of system in terms of the damping and stiffness for this sort of generic second order transfer function. Further, what we're going to do is to keep things a little bit exciting, we're going to look at the regulation example. Okay, remember the regulation control objective is basically where you want to maintain, you want to keep y of t as close to the reference signal as possible. You want to maintain the output following the input. In other words, assume that you're already tracking and you want to keep it that way even when there's a non-zero external disturbance. Okay, so the regulation control objective is such that you want to maintain the tracking objective in the face of some unwanted disturbance forces. Okay, now to analyze the closed loop response for the regulation control objective, the closed loop transfer function that we want to consider would be the transfer function from W to Y. Okay, this transfer function will allow us to see how a disturbance of like W affects the closed loop output Y. And from lecture 6, where we analyzed the closed loop control structure, we basically developed a matrix of transfer function numerators so that we can quickly see what this relationship is. If you consult that matrix, or if you just simply do the block diagram algebra, you'll find very quickly that the transfer function is P over 1 plus Cp. It's not that critical that we're discussing the regulation example because remember the closed loop denominator is always going to be the same. It's the characteristic equation for that closed loop system. Okay, so what we're going to do now is basically consider a couple of different control options. So for proportional control, what we have is that C of S is just equal to K. It's just equal to some control gain, which we'll call KP. And if we plug this plant transfer function and this controller into the regulation transfer function, which is a transfer function from W to Y, we just have to plug into the expression P over 1 plus CP. Okay, so for P control, what we're going to get is that H of S is equal to 1 over ms squared plus cs plus k plus kp. And all I've done here is written down the result of literally plugging in C and P into this expression here. Okay, so I won't bore you with the algebra to get here, but what I'm showing you here is basically the closed loop transfer function. What I'm showing you here is essentially the closed loop transfer function from W to Y, which is the transfer function that we're considering for this example. The point I'm trying to make here is, okay, so let's bring it full circle. We were originally talking about this open loop transfer function in terms of its damping term and its stiffness term here, right? Once we close the loop and apply feedback control, if we use a controller that's a pure gain value, right? So just proportional control, C of S is equal to KP, then our closed loop transfer function looks like this. It's H of S, right? And what you notice is that the only term that has been affected is the stiffness term. Okay, so it's gone from K to the quantity K plus KP. The damping term hasn't changed, and the mass hasn't changed. Right? So if you use proportional control, you are effectively increasing the stiffness in the system. Okay, so the proportional controller effectively just increases the stiffness in that particular system. Okay, another way to see that is it's basically as though you unbolted the spring from this system, right? It's basically like you unbolted the spring and put in a new spring, and the spring coefficient or the spring constant for this spring has the value of K plus KP, where KP is adjustable. That's based on the gain that you choose. Okay, so it's almost like you're just replacing the spring in the system with a heavier spring, which is K plus KP. Except you're not physically doing that. You're doing that in control. You're doing that through the feedback structure. Okay. What this results in, this has a couple of implications down the line. Okay, so proportional control has the effect of increasing the stiffness. Well, how does that correspond to the system response? What we know about the system response is that it's highly characterized by the poles of the transfer function, right? The poles of a system basically dictate the behavior of a system. So if we look at the poles of this transfer function, well, what are they? The poles of H of S we can find by simply applying the quadratic formula to the denominator. So S is going to be equal to minus C plus or minus square root C squared minus 4m k plus kp, all divided by 2m. And what we want to do, okay, notice that this quadratic solution could either be two real values or two complex values. And we already know that a pair of real poles is just going to be the sum of two exponentially decaying responses, which isn't that interesting. What we want to do is analyze, well, essentially, what is the path of the poles in the S-plane when the poles are complex? Okay, so the poles themselves, depending on your choice of C, M, and K, and KP in this case, could either be two real poles or two complex poles. The scenario when the poles are both real is not very interesting. So we're going to consider that basically if Kp is large enough, for a sufficiently large value for Kp, we can essentially neglect the c squared term, right? Essentially, we can neglect that term, and then the poles, can be approximated by the following: minus c over 2m, that's the real component, plus or minus, now it's going to be plus or minus root k plus kp over m as the imaginary component. Okay, so this, if Kp is large enough, you're going to produce two complex poles, and these are them. Okay, so it's approximately minus c over 2m plus or minus root k plus kp over mj. The point of this exercise, okay, is not just to show you here's some arbitrary poles of a generalized transfer function. The idea is to see, well, how do these poles move in the S-plane as you increase that gain parameter Kp. Okay, so in the S-plane, which again, remember, is just the complex plane, but it's the domain in which the poles live, so we call that the S-plane. Look at the form of this set of poles. Okay, so you've got real and you've got your imaginary component of the poles. The real component of the poles is minus c over 2m. That's it. It's fixed, right? So the real component of the pole never actually changes. It's the imaginary component of the pole that is increased as you increase Kp. So if you imagine the trajectory of the poles in the S-plane as you increase that gain parameter, what you might expect is to see a pair of complex poles that such that the imaginary component increases as you turn up that gain parameter. Okay, so the trajectory of the poles is actually like this. They move vertically away from the real axis as you turn up the proportional control parameter. Okay, I want you to let this sink in for just a second. Okay, what you're visualizing here on this plot is basically the closed loop pole location as you turn up that gain. Okay, so as you turn up that gain Kp, you are actually changing the location of the closed loop poles. And if you change the location of the closed loop poles, you're going to influence the system behavior. And for this particular controller, it looks as though the closed loop poles traverse along these branches, right? These blue vertical lines. What this means, the implication here, we can take this a step further. And so for any arbitrary point on that blue line, you can do some analysis. You can say, well, what is, for example, omega n? Well, omega n is the distance from the origin to that particular pole. So if I increase the control parameter Kp, my poles are moving further away from the real axis along these vertical lines. Well, omega n is also increasing. Okay, so if Kp increases, omega n increases. And if the undamped natural frequency increases, you are actually going to see more oscillations. Okay, you're going to see this is where the faster response comes from. Right? Because if you have a sine wave that oscillates very slowly, well, this is a relatively slow response, right? Stuff doesn't happen right away. But if your frequency of oscillation is very high, if you have a high frequency of oscillation, you have a scenario where you have a very fast response. Okay, so that's what we're tying together here is the effect of increasing that control parameter Kp. You're getting a larger omega n, and therefore you get faster response. But also other things are happening, right? If you look at the angle as measured from the imaginary axis, the angle is going to get smaller and smaller as these poles traverse up these blue lines. So beta is actually going to decrease. And if beta decreases, then so does the damping ratio zeta. So as you increase Kp, zeta is actually getting smaller and smaller, which means there is less effective damping in the system. And if there's less effective damping in the system, you're going to get more oscillation in the system. Lastly, remember that the pole location is defined by, right, so that generally speaking, the pole location is minus sigma plus or minus j omega, where sigma is the real component of the pole. The real component of the pole, as you increase Kp, is not affected. Okay, so sigma itself is unchanged. Right, so sigma is unaffected by increasing or decreasing Kp. And if sigma is unaffected by increasing or decreasing Kp, then the settling time is unaffected by increasing or decreasing Kp. Because recall that the settling time, or the rate of convergence of a response, is a function of sigma and the e to the minus sigma t envelope function that's defined by that real component of the pole. Okay, so if sigma is unchanged by Kp, then also the settling time is unchanged, and therefore the rate of convergence is unaffected by Kp, which is something interesting to note, because if you're trying to get a system to settle down faster and converge to its final value, well, this little analysis here would tell you that adjusting the spring coefficient or the spring stiffness, or conversely using a proportional control scheme, is not going to achieve that goal. You will not influence the settling time by adjusting the proportional gain. Okay, so all of this we can get from doing this little bit of analysis on the closed loop poles for a proportional controller. Okay, so let's just take a look at what we did here. We started with a general second order system. We defined the damping and stiffness term. Then we said, here's a closed loop transfer function we're going to analyze. It's just for regulation, is P over 1 plus Cp. And then we said, all right, what happens if we use a proportional controller? If we use a proportional controller, well, this is all the stuff that happens, right? If we use proportional control and we increase Kp, we get faster response, which is what we said initially at the high level. But we also see that zeta decreases, therefore we see more oscillation in the response, and also the settling time is unchanged. All of that goes with using a proportional controller. So let's now see what happens in the same context. What happens if we use derivative control? Okay, so what happens if we use a controller of the form, not just Kp, but this time is Kd times S. Okay, so it's just a different form of the transfer function for the controller, but I think you're going to see that it's got some very different influences on the closed loop system. Okay, so just like we did before, we're going to plug into the same transfer function, h of s, where P hasn't changed. The P is just the same second order plant from above, but the controller has changed. It's not just Kp, it's now Kd times S. And when you plug into this transfer function, you actually get a different transfer function. So it's ms squared as before, plus now notice where the Kd term settles in the closed loop denominator. The Kd term actually now is grouped together with the original damping term. So derivative control, right, the Kd term, this has the effect of influencing the effective damping in the system. And like I said before, it's as though you physically went in and unbolted the original damper and bolted in a heavier damper with a coefficient C plus Kd. Right? So instead of doing that physically, you're just using feedback control to achieve that same effective output as though you were increasing the effective damping in the system. Okay, so derivative control has the effect of increasing the effective damping in the system. How does that translate to the system response? Well, we can do the same type of analysis we did before, is to look at the poles of that system, where we're still going to use a quadratic formula to solve, but it's just going to look a little bit different because the denominator is effectively different. So it ends up being like minus C plus KD plus or minus square root of C plus KD squared minus 4mk all over 2m. Now what you can see here is that unlike the case for proportional control, KD is going to find itself into both the real and imaginary component of the pole. Okay, so it's not a case of the poles just moving vertically in the S-plane anymore, right? You have to think about, well, if you increase KD, you're influencing both the real and imaginary components of the poles. Okay, and the way that the sort of trajectory of the closed loop poles looks in the S-plane is the following. Okay, so as I increase KD, the poles actually move in this fashion. So imagining that they just start in some arbitrary point in the complex plane, the poles actually do something like this. So one pole is going to sort of, the imaginary part will shrink and the real part will get more negative. So the combination of the two makes this sort of curved trajectory in the S-plane. And actually, the other pole on the other side is going to be doing the same thing, just mirrored, because if you look at the form, it's always a plus or minus the imaginary component, right? So the complex poles are always going to exist in complex conjugates. And so what you end up having is that while the poles are in the complex space, this is how they're going to move throughout the S-plane. Once, if you notice, once KD is large enough, then you're not going to have complex poles anymore. Like if C plus KD squared is greater than 4mk, then you're going to end up with two real poles. And it turns out that the complex poles will meet at the same location on the real axis, and then one of the poles is going to head off in one direction, and then the other pole is going to go in the opposite direction. But again, this part is not very interesting. When the poles are both real, we know that the response is just going to be the sum of two exponentially decaying responses. So that's not that interesting. The interesting stuff happens when the poles are out in the complex space and they're moving around in this fashion. So that's the part that we're going to analyze now. So while the poles are complex, what we can see is the following. Okay, so what we can see as the poles are complex is, well, we can see a couple of things. We can see first of all that, okay, so if we have a pole here, if we look at a line that sort of passes through it, we can see that the angle measured from the imaginary axis is actually increasing. So as we increase KD, our poles are moving along this curved path, so the angle is actually increasing. And if the angle increases, that means that zeta is also increasing. So this should be no surprise because zeta is the damping ratio, right? It's a measure of the effective damping in the system. Well, by increasing KD, we are essentially increasing the overall damping coefficient in the transfer function. So it stands to reason that zeta should increase. Okay, so what we can do is sort of compile all of our findings like we did for proportional control. So as KD increases, beta increases, and therefore zeta increases. And if zeta increases, if the overall damping in the system increases, we get fewer oscillations. We get fewer oscillations in the response, and therefore, generally, this corresponds to a smoother response. Right? So as opposed to a response that looks like this, right, with lots of oscillations, we may see something like this, fewer oscillations, which is the result of increasing the zeta in the system, but also it's a much nicer response. It's smoother, right? Okay. Additionally, what we saw in the case of the proportional controller up here is that there was no effect on sigma. The real part of the pole never changed because these poles just moved vertically away from each other, which means that the settling time was unaffected by proportional control. In this case, what we're seeing is that as we increase KD, the real component of the pole is actually moving to the left. Okay, so sigma is actually increasing as we increase KD. And if sigma increases, that means that we get faster settling time, right? So if sigma increases, that means our settling time comes down, which means that we get faster convergence. Remember, the settling time is the amount of time it takes for our response to be within plus or minus 1 or plus or minus 2% of the final value. So the settling time is a measure of the speed of convergence. And as we're seeing here, if you increase KD, you're getting the real component of the poles to move faster, to decay faster, right? So the real component is moving to the left, and therefore the response is decaying faster, yielding a faster convergence, which is the original, right? So way at the top, that's what we said the primary function of the derivative gain is, to give us faster convergence. Well, this is why, right? So when we dig a little bit deeper, this is the actual reason. It's because we're pushing the real component of the poles further to the left. Okay, so this is the effect of KD down at the level of the poles of the system. So when we start to combine these effects of the controller, okay, so if we were to summarize so far, well, let's use a combination of the two. If we were to do a controller like this, and by the way, this is called PD control, right? It's basically PID control without the I. PD control is actually a very popular subset of the PID controller, precisely for the reasons above, right? It allows us to influence the essentially the pole location for the closed loop system very easily, because we'll just follow essentially these patterns for how the poles move in the S-plane. And then when we combine them together into one controller, we have pretty decent control over where we can place the poles. If we were to, right, so to sort of summarize here, if we were to wrap things up for this segment by computing the same transfer function as we did before, P over 1 plus CP, using this new controller, a combination of the proportional and the derivative controller, what you find is that this is the resulting transfer function. And it's actually pretty nice. What we see here is that the proportional gain only influences the stiffness term, and the derivative controller, the derivative gain only influences the damping term. So you almost have independent control over the stiffness term and the damping term, which is very nice when it comes to control design, because that means effectively you can basically adjust the closed loop pole location in the S-plane by adjusting those two terms individually. So you get the increased stiffness, which gives you the faster response due to the proportional gain, but you also get the ability to improve the damping and adjust the sigma value, which gives you the faster rate of convergence. So it's like you get the best of both worlds by using the PD control. Okay. You'll notice that I haven't mentioned anything about the integral control yet, and that's because the integral controller is a bit of a different beast altogether. Okay, if we take a look at this H of S, what you find is that something called pole placement is relatively easy. Right, you have independent control over the damping and the stiffness term. So placing the poles in the S-plane wherever you want is actually pretty easy. If you notice, look at the okay, I strategically call this transfer function H. Look at the numerator of this transfer function. It is just a constant value. There's no zeros in the transfer function for H, And clearly there are no zeros at the origin in H because there are simply no zeros. So using PD control is nice because you have that flexibility to place the poles where you want. However, you have yourself a type 0 system because there are no poles, there are no zeros at the origin in H. So this is a great controller for improving the transient portion of the response, but it can't do anything for you regarding the steady state response. Right? It can't help you track a step reference better at all. So the KD and the KP term, you can mess with those all you want, but it's not going to help you track a particular reference with zero steady state error, right? Because we have not influenced the system type. And of course, that's where the integral gain is going to come into play. The integral gain is used, as we mentioned above, for improving the steady state performance. So if we now look at I control, the integral control, we're not going to do the same type of regulation example with the mass spring damper system here. We're going to look at integral control from a slightly different perspective. Integral control as a form of Ki over S. And really all we need to do here is to compute that same transfer function. Okay, so if we plug into P over 1 plus Cp, do the math and plug in this updated controller to the same plant above, what you end up seeing is that H of S actually works out to look like this. So you get a cubic denominator, and so let me just finish writing it out. Your sort of analogy of increasing the effective stiffness and the effective damping, that whole thing kind of goes away because now we're dealing with a third order denominator. Okay, so Ki appears in the third order denominator as a constant value, but you still have this ms cubed in the denominator. So it becomes third order. Talking about the effective stiffness and damping doesn't really work anymore. However, the thing that should stand out immediately is that by using this controller, we've now placed an S in the numerator of the H of S transfer function. Okay, so just like before in the system type lecture, this would indicate that we have 1 0 at the origin, and therefore we have bumped up the system type to a type 1 from a type 0, which in this case, since we're talking about regulation, will allow us to reject a step disturbance perfectly. Right? We could do the same analysis all over again for the tracking control objective, and we would find that because H of S is now type 1, now we're capable of tracking a step reference with zero steady state error. Okay, this is basically the entire benefit of using integral control, is to bump up the system type so that you can track more complex types of references, or so that you can reject more complex types of disturbances. Now the thing about integral control is that you've got to be a little bit careful, because primarily just by looking at this denominator, noting that it's become third order, some things should pop off in your head. You should basically see a red flag in that, I'd better address stability a little bit more carefully. Whereas in the previous two cases, with derivative control and in the case of proportional control, we just had a second order system. So we didn't alter the order of the system at all. And so therefore, to address the closed loop stability, all we had to do is guarantee that all the coefficients were strictly positive. Right? So as long as the mass and the damping term and the stiffness term are all positive, you can guarantee closed loop stability. What we know about stability is that when things are third order and higher, it's a little bit more complicated than just making sure all the coefficients are positive, right? If all the coefficients are positive, all that means is that it satisfies the necessary condition, but it doesn't imply that the system is stable. So looking back to our lecture 5 where we discussed stability, what this means is that we actually have to apply some type of analysis to guarantee or to look at the nature of the stability for this third order system. And one of the tools that we've developed is the Routh stability criterion. Okay? So if we look at the Routh test for this third order system, it's pretty straightforward, right? We're going to get the first two rows by looking at the denominator. So we've got an M, a C. We start a new column, K, Ki, and that's it. There's only four terms, right? So trivial 0, trivial 0. This is the first part of the Routh table. What we have to do is to populate the rest of the table. So we need to compute the B row and the C row. And when we do that, we get an element in the first column here that looks like this, trivial 0 here, and then a Ki value here, trivial 0, and that would complete the first, that would complete the table. And so this is the first column of the Routh table here. What you can see is that in order to guarantee stability of this system using integral control, well, we need the mass to be positive. That's kind of a given. We need the damping coefficient to be positive. We also need the integral gain itself to be positive, but this is one that's a little bit interesting. Okay, so Ki definitely needs to be greater than 0, but also from this term here, we produce a secondary constraint on Ki. Right? If Ck minus Mki needs to be greater than 0, that would imply that Ki itself needs to be less than Ck over M. So putting these two constraints together, you'd find that in order to guarantee closed loop stability, there's a very finite range for what Ki can be. Okay, so if Ki is within this range, greater than 0 but less than Ck over M, then I will guarantee closed loop stability, which is slightly limiting, right? So if Ki falls outside of this range, by definition, you will actually destabilize the system. And so this is another case where it's very important that you pay attention to the stability once you start incorporating integral controllers. Okay? We can actually do a similar thing. Okay? Even though we have a third order denominator, we can still analyze how the poles of this third order system move around in the S-plane. And I don't mean to get too far ahead of you. We're actually going to discuss this sort of business of how the poles move around in the S-plane. This is a concept known as the root locus, which we're going to study starting next lecture. I'm jumping a little bit ahead because I want to demonstrate the effects of these PID gains, but we haven't really talked about that root locus tool yet. Nonetheless, I think it's it's easy enough to comprehend that as I increase Ki, these sort of lines in the S-plane represent how the closed loop poles are going to move. Okay, so if we were to look at the root locus for the case of using an integral control like this, that ends up looking like the following. So here's our real axis, imaginary axis. This is the S-plane. Okay, when Ki equals 0, okay, imagine that Ki is zeroed out and we basically have no control. Ki equals 0 actually means that we could factor out an S from the ms cubed plus cs squared plus ks, which means we'd have one pole at the origin, right? So when Ki is 0, there is actually a pole at the origin. Right? When Ki is 0, there's a pole at the origin, and there's two other complex poles somewhere out in the stable region. Okay, this is actually what corresponds to our lower limit. So when Ki equals 0, we have one pole. It's right on the cusp of going unstable, but it's not. It's marginally stable. Now here's what happens. As we increase Ki, these three poles, remember there's three poles now because the denominator is third order. These three poles are going to move in this fashion. So the pole along the real axis, that's going to traverse further and further and further to the left along the real axis like so. But the other two poles, right, the other two poles are going to move in a different way. And they're going to move like this. Okay, so these poles are going to sort of go to the right like so. As we increase Ki, and as we keep increasing that gain, at some point we are going to exceed the upper limit for stability. What that corresponds to is that these two branches will actually intersect the imaginary axis. And any value of Ki larger than Ck over m is going to place these two branches to the right of the imaginary axis. Okay, so as we increase our Ki too large, right? So if Ki is too large, we're going to get the case that, okay, so this may be the location of the three poles. This guy is fine. This guy is just getting more stable as you increase Ki. But it's these two poles here that are the problem. Because at that critical value of Ki, which is Ck over m, you're going to place those two poles right on the imaginary axis. And if you crank Ki up any more than that, you're going to push those two poles into the right half plane, thereby destabilizing the system. This illustration highlights a couple of things. Okay, it illustrates first and foremost that you do need to be extra careful when you're using integral control because it's very easy to destabilize your system, right? It also illustrates another point. Okay, so the fact of the matter is, as long as as long as all the poles are stable, we can still do a similar type of analysis that we've been doing for the previous two controllers, the proportional and the derivative. As long as the poles are stable, the pair of complex poles are going to see the following. We're going to see that beta decreases, right? So the angle measured from the vertical is going to decrease as we increase the integral gain. And again, we get the scenario where we are going to effectively reduce the damping ratio zeta. If we increase Ki, what we're going to see is again that beta decreases and therefore zeta decreases. Anytime you reduce zeta, you're reducing the damping ratio in the system, which means you're going to introduce more oscillations into the system, right? Introducing more oscillations into the system is usually not desired, right? I can't think of any practical control system where you want more oscillations rather than less, right? Imagine getting into an elevator and pushing the third floor, going past the third floor, going below the third floor, and sort of oscillating to hunt to find that third floor before the doors open and it finally lets you out, right? Oscillations in a system response are usually just a fact of life. We have to live with them to get the desired result, but you don't usually want more oscillations. Okay, so the trade-off here is, okay, unfortunately I am increasing, unfortunately by increasing the integral gain, I am introducing more oscillations into the system, but the benefit of increasing Ki is that I get that bump in system type. So I get better tracking or better disturbance rejection at the expense of a slightly worse transient response. Okay, so just like in almost every other aspect of control system design, there's always this balance of forces in play. Okay, so if you want to use the integral gain to get better tracking or better disturbance rejection, you may have to suffer a little bit by introducing more oscillation into your response. Which, okay, and then once you get better at tuning PID controllers, you introduce the integral gain, you introduce more oscillations, but then strategically you could bump up the derivative gain even more. So you use more derivative gain, which is supposed to reduce the number of oscillations. Okay, so you get all these different sort of fighting results by using the three different gains, Kp, Ki, and Kd. And the only way to really do any intelligent PID control is to understand the underlying effect of each one of those three gains. Okay, so pretty much what I did up until now is I gave you an overview of what each component or each term of the three-term PID controller is supposed to do, down to the level of the closed loop pole trajectory in the S-plane, which to me is a good enough start to be able to do some actual control design. Keep in mind that this is a very high level overview of PID control. You can almost write an entire class on doing PID control tuning. I'm just serving what I'm trying to do is serve you by giving you a broad enough overview so that you understand the basics, and then once you want to get into a finer level of detail of PID tuning, you can find those algorithms and methods yourself. Okay, so this is sort of your introduction into PID control, at least the conceptual part. Before we end, I want to give you some practical usage of these concepts. Okay, so I don't want to just leave you with here's the theory behind PID control. I want to give you some actual tools that you can use to develop control systems. Okay. Okay, so there's generally two avenues of, if you zoom really far out, okay, there's generally two avenues of doing control design, and they kind of get the path kind of splits when either you know the plant or when you don't know the plant. Okay, so basically PID control with known plant. Okay, so if you know the plant, then there's sort of one way to do things. But if you don't know the plant, then there's actually another way to do it. And I just want to sort of highlight the differences here because there's a bit of a disconnect when it comes to understanding how control systems work, specifically as to how they are applied in real life. Okay, so everything you're learning in a fundamental controls course like this, like 99% of everything we're doing in this class assumes that you know the transfer function for the system, right? We spent a lot of time doing modeling and developing transfer function representations for dynamic systems. So naturally, all the theoretical tools that we develop, they're going to be based around knowing that transfer function. For instance, right, when we do something like the unity feedback control structure, we're assuming that we know both the controller and the plant. And if we know both of those things, then we can do sort of, closed loop control analysis, like, for example, developing the closed loop transfer function CP over 1 plus CP. Now you can imagine if you didn't have the transfer function for the open loop plant, if you didn't have P of S, you couldn't compute G of S. And if you can't compute G of S, then you can't do pole analysis or the Routh test or things like that. Okay, so if you know the plant, then all of the tools that we've been developing up until now, those all apply. And for any real life system, at the start of the design, you just have to ask yourself essentially, do you want to spend the time to model that system and develop a differential equation or a transfer function for that system? If you are willing to spend the time, then you can do this type of analysis where you can look at the closed loop system transfer function, look at the closed loop poles, look at things like the Routh test for designing for stability and so forth. Okay, so you can do all those things as long as you have a model for the system, like a transfer function. Okay, however, there's like this whole other world of control design where you do control design without ever having a transfer function available. Okay, so some systems are just too complicated to try to model, or perhaps you're on a time schedule, right? You're on a time crunch and you don't want to spend the required time necessary to model that system, right? You want to just get right into the control design, which in some cases is totally valid. And in PID control, that's one of those scenarios where it's generally acceptable to attempt to do control design even if you don't have the plant modeled as a transfer function. For instance, like the HVAC systems that regulate the temperature in our buildings, in our homes, in our hospitals, in our schools. It's not as though the engineers that designed those systems have modeled, the entire heat transfer characteristics of that particular space. Rather, what ends up happening is they assume the form of the controller. They're going to use PID control, and the technicians that install those systems are so well versed in the inner workings of that particular controller that they can actually tune that system based on the input output data without ever needing to identify the plant. Okay, so I just want to highlight that there's basically these two big main avenues of doing control design. in one scenario you have a model for the transfer function, and then all of these analytical tools are available to you. But the drawback there is it takes some time to be able to identify a particular system and develop a transfer function. On the flip side, if you don't have the resources available to model the system, you can still do pretty decent control design if you use certain control algorithms that are well documented, like the PID control. So this is sort of, this area here is what I want to focus on for the rest of the lecture. And this is sort of the one departure in this course from doing control design based on a known plant. Okay, so for the subsequent example here, we're not going to assume that we know the plant, and we're still going to be able to do some control design. Okay, so the picture, essentially the picture for the visual that you should have in your head for wanting to do control design for an unknown plant looks like this, right? You still know a few things. You still know that you're going to apply some PID controller that goes in this control block. You still know that you're going to do unity feedback control, where you feedback the measurement as a negative feedback. And you still know that the measured output is going to be Y. The only thing you don't know is what's actually in the transfer function. Okay, so if you don't know this actual transfer function, then that also means that you don't know the closed loop transfer function, which means you can't do things like the Routh stability criterion. Okay, however, in this scenario, if C of S, if this is a PID controller, the same controller that we've been talking about this entire lecture, if that's the case, then there are actually several methods for tuning that particular controller available to you. What I'm going to show you today is basically two methods, right? So I'm going to show you two methods for tuning PID gains, but just be aware that there's several different methods, and they all have their their benefits and drawbacks. Okay, so what I'm going to show you today is something called Ziegler-Nichols PID tuning. Ziegler-Nichols, these were two people, these were two engineers who developed these algorithms for tuning the PID gains before there were numerical tools like MATLAB and Simulink, where you can just go in and design it all on the computer and then deploy it at a later time. You have to remember that when these algorithms were developed, the concept of feedback control was well established, but the tools available to those engineers were minimal. There were no computers, there was no MATLAB, there was no numerical simulation at that time. So they had to develop ways to basically come up with control algorithms. And so I'm going to show you two different methods that these guys came up with. And really, these methods are still widely used even today. Okay, so like I said, the benefit of having a computer and numerical simulation package like MATLAB and Simulink, the benefit there is if you know the model, if you have a model for the system, like a transfer function or set of ODEs, then a numerical package like MATLAB and Simulink is super helpful, right? But if you don't have the plant, right? Again, if we're working with an unknown plant, then you still have to resort to some type of educated guess and check procedure, which is ultimately what the Ziegler-Nichols PID tuning algorithms are, right? Ultimately, instead of just playing around with the three gains, P, I, and D, you want to go through a very structured procedure so that you can systematically design a decent PID controller. Okay, so the first method I'm going to show you is called ultimate sensitivity. And the second method I'm going to show you is something called the quarter decay. Quarter decay method. Okay, so two different methods for developing essentially a set of gains, right? The outcome of these processes is basically a Kp value, a Ki value, and a Kd value that you're going to plug into your control system. Okay, so the way this works is it's a step-by-step process, right? So what you're going to do is you're going to zero out the integral and derivative terms. So you're only working with proportional control, right? So zero those out, and actually that's the same for both methods. So regardless of which method you're using, you're only going to mess around with Kp first. Once you zero out Ki and Kd, then what you're going to do is you're going to increase Kp until you see a particular phenomenon occur in the unit step response. Okay, so for Kp, you're gonna keep increasing it until until you basically have sustained oscillation. So it's called ultimate sensitivity because Kp is really increased until you're bordering on instability. So what you want to see in your output is essentially the following. You want to basically just see pure oscillation, sustained output, marginally stable output. Okay. Once you find the Kp value that produces this phenomenon, then you're going to make a couple of definitions. And one is called the ultimate gain, Ku. And for the ultimate sensitivity method, the ultimate gain, Ku, is equal to the Kp that generated the phenomenon above. So Ku is just equal to the Kp that you just determined. You also need to define something called the ultimate period. And this you're going to have to go into the actual recorded data and extract it. Okay, so the ultimate period is essentially once you establish this sustained oscillations, you just take any peak to peak time to figure out the ultimate period. Okay, and then once you figure out the ultimate gain and ultimate period, then you go over here and you plug into the set of equations that gives you your final set of PID gains to actually use in your control scheme. Okay, so Kp is equal to 0.1 of the ultimate gain, which was the Kp used to produce this phenomenon. Ki is determined by this equation, just 2 times Kp divided by Tu as measured in seconds. Okay, so Kp now, 2 times Kp, that's not this Kp that was used to generate the ultimate sensitivity or the marginal stability. This Kp is actually the one that you just computed here. Okay, and then finally Kd is equal to Kp, again the same Kp that you just computed, times Tu as measured in seconds divided by 8. Okay, and then now this set of gains, when you go to implement it, should give you a decent starting point for that control system. And then from there, you can fine tune the parameters, Kp, Ki, and Kd, to really hone your response however you'd like, based on your knowledge of how each of those 3 gains is supposed to impact the output. Okay. In some cases, the system is just the nature of the dynamics of the system are such that you simply can't produce sustained oscillations in the output. Some systems, if it's for example, if it's a first order system and you're using a proportional controller, you will never produce sustained oscillations with a unit step response, right? Unit step input, right? That's what this response is, okay? Because it's first order and it has real poles, okay? So in that case, okay, let me just back up for a second. If you find that you are unable to produce sustained oscillations, you can also try this other method. It's called the quarter decay method. All right. The quarter decay method again starts by setting the integral and derivative term to 0, and then again you're going to increase Kp until you see a certain phenomenon. Okay. And that phenomenon is different this time. So the phenomenon for the quarter decay looks like this, and it does not rely on producing sustained oscillations. Okay, so your typical step response will look something like this. Something like this, right? So you get some oscillations which eventually decay and you reach some steady state value. The quarter decay phenomenon, so you're going to keep increasing Kp until you see the following. What you're looking for is for the height of the first peak with respect to the final value, the ratio of, in fact, it's the ratio of the height of the second peak, which we can call B, to the first peak. You want that ratio to equal 1/4 or 1/4. Okay, so the ratio of B over A, you're looking for that to equal about 1/4. And that's the quarter decay phenomenon, right? And remember, the key here is it's not the actual height of the max value of A. It's not the peak of B divided by the peak of A. It's the distance between the peak of B from the final value, which is here, divided by the distance for the first peak to the final value. That's the distance A. Okay. Then once you get that phenomenon, then again you're going to define the ultimate gain and ultimate period. And the only difference here is that the ultimate gain for the quarter decay method just happens to be twice the gain that you use to produce the quarter decay phenomenon. Again, the ultimate period, that's still, you're going to get that from the data. Right? And from data, what I mean is, to do PID tuning, you are actually implementing the closed loop system in real time, so you can actually record the output data. Okay, so you'll actually see some type of response that looks like this, yellow plot that I've drawn, and you've actually got to go in there and sort out what the ultimate period is based on looking at the peak to peak time. Okay, and then again, once you have those two parameters, the ultimate gain, ultimate period, you just plug those back into the same set of three equations to produce your PID gains. These are two completely separate methods, and they generally both give you a pretty decent closed loop response. Okay? The last thing I want to do is to set up an example where I show you how to implement both of these tuning methods, so you can see real time how to do sort of a PID tuning control design. Okay, so what we're going to do is we're going to start with just a somewhat arbitrary third order plant. Okay, so this is the plant that that we're going to tune to. Now I do have to mention a couple of things here. Okay, and the first one is right off the bat, I mentioned that the PID tuning procedures, like the two Ziegler-Nichols methods that I just showed you, those do not rely on knowing the plant model. Okay, you can do that on just a black box system and just look at the output, right? All you have to do is the only metric for tuning the system, remember, is looking at the unit step response. So whether or not you have marginal stability or this quarter decay phenomenon. However, for this example, the first thing that I did was to define a transfer function, right? So the reason for this, okay, is that I do not have a physical system in front of me to do PID control on. Okay, so what I have to do is I have to fabricate a system, okay, virtually, and this is how I'm doing it. So I'm just defining some arbitrary transfer function. I'm going to define this in MATLAB, but then I'm never going to touch it again. Okay, so I'm never going to like look at the poles of this, or I'm never going to compute a transfer function based on this plant. But I do need some type of dynamic behavior to exist so that I can do PID control. Okay, so what you can see is in MATLAB, this little script basically defines that transfer function that I just wrote down. It's a 1 over s cubed plus 9s squared plus 23s plus 15. Really is purely just a made-up transfer function. But this does represent what a real system might be. Okay, so there's some real system that you want to tune a PID controller for. That's what all this represents. Now we're just going to put this away, and we're never really going to do anything with it, right? We're never going to use those coefficients to do any numerical computation. One thing I will show you is the following. So what I'm showing you here is the unit. This is the unit step input for the open loop transfer function. Okay, so if I apply a unit step input, basically a value of u is equal to 1, this is what you get in the output. Notice the response. Okay, so this response is actually, it looks pretty unassuming, but it's actually a horrible response. First of all, note the final value. The final value is something like, 0.06, somewhere between 0.06 and 0.07. Okay, so if I were trying to track a unit step reference, like r equals 1, and I only made it to 0.06, then I am tracking horribly. I'm nowhere near a value of 1, which is where I want to be, right? Also, pay attention to how long it takes before it reaches steady state. Okay, it reaches steady state after roughly 250 seconds. Okay, so it's a very, very slow moving dynamic plant. And this is just not acceptable for whatever, whatever application we want to whatever application this represents. And so this is sort of the motivating feature for why we're going to use control in the first place, right? We want to be able to track a step reference perfectly, right, for this system, and we want it to respond faster than, 250 seconds. Okay, so that's why we're going to do feedback control on this system, just as a little bit of motivation. Now, the way I have this script set up is the following. I have basically the three control knobs here, so we can define PID gains however we'd like, and this is what we're going to actually use to tune the gains. In each of these other cells, what I'm doing is after I define the PID gains, I'm simulating a closed loop step response. And the way I'm simulating it is to use Simulink, which is a built-in sort of plugin or built-in program within MATLAB that allows you to do block diagram programming. Okay, so this is my Simulink model that represents the closed loop transfer function from the step reference R to the output Y. And what you're seeing here in this area, all of this stuff is the PID controller, where you've got KP as just the gain, KI scales the integrator, so it's KI over S, and then this whole section here represents the derivative portion of the controller. Now I know this is going to look a little bit strange because actually all of this stuff here represents 100 KDS divided by S plus 100. So that's very different from just KDS, which is what our entire theoretical basis for the derivative control was based on, right? So I do need to spend a minute explaining that. Okay, so this portion of the control, what's going on there? Well, for the KD term, okay, the derivative controller, remember, has the form of KD times S. Okay, that's the derivative part of the controller. Now, in theory, it's fine to base all of our analysis on this form of the controller, but you have to remember in practice, in real world applications, everything has to be causal. In other words, our real life experiences all adhere to the causal notion, which basically just means that the current output is only a function of current and past inputs, and that's it. There's never going to be a case where the current output is dependent on some unknown future input. And if you recall back from lecture 3 when we talked about the causality of a transfer function, that corresponds to the order of the denominator polynomial having to be equal to or greater than that of the numerator. So if you look at just KDS by itself, this is a non-causal system because the denominator has order 0, the numerator has order 1. Right? So 1 is basically like s to the 0, and in the numerator we have s to the 1. But we need the denominator to be greater than or equal to the numerator. So that's a problem right there. Theoretically, it's fine to base our analysis off the non-causal version, but when we go to do even a numerical simulation in MATLAB, if you try to implement just KDS by itself, it will give you an error. It will say it's non-causal effectively. Okay, so one way to get around this is to actually put this in series with a low-pass filter. Okay, and so the real way to implement derivative control is, yeah, you start with KDS, but you also multiply by an alpha over S plus alpha. And alpha over S plus alpha, as you may know, has the form of a low-pass first order low-pass filter. And what that does is a couple of things. So if you look at this term as a whole now, well, first of all, now it's causal because I have a first order numerator and a first order denominator. So it becomes a causal system as a whole. And the other thing that it solves is actually the fact that we place the derivative term in line with the low pass filter, it actually helps on two fronts because, and this is almost a topic for another lecture, but the derivative portion of the PID control, um, it tends to amplify any high frequency sensor noise that may exist in the system. Okay, so theoretically, remember the derivative term serves to smooth out the response, but what ends up happening is if there's any high frequency noise in the system, right? If there's noise that looks like this and is high frequency, the derivatives of each of these, right, the derivative, the slopes of this high frequency noise, those are extremely large. And if you have any amount of scaling of the derivative of that signal, then the entire derivative term sort of grows disproportionately. Okay, so it's kind of a problem when you have lots of high frequency noise to use a large value of KD because you actually end up amplifying a lot of that noise, and that can cause problems down the line as well. So the fact that we put the derivative term in a low pass in series with a low pass filter also helps to squash down some of that high frequency sensor noise. If you choose your cutoff frequency intelligently, you can actually eliminate some of that high frequency sensor noise and reduce the amount of amplification that you see. Okay, so that's a little side tangent on the derivative control, but that's what you're seeing here. This is an implementation of 100 kds over s plus 100, where alpha is essentially equal to a value of 100. Okay, so again, this entire thing here, this represents your controller. This is your PID controller. Notice that the plant is defined in Simulink, but it simply exists there as some dynamic relationship. We're never going to actually, we're never going to actually analyze the poles of that or look at a Routh test of the closed loop system or anything like that. So this just exists there as the actual dynamic system that we want to tune. And as I was saying before, this cell will actually run that simulation and then just make a couple of plots so that we can see what our PID tuning is actually doing. Okay, so without further ado, let's go ahead and tune this PID controller. Remember, if we're going to use the ultimate sensitivity method, what we're trying to do is zero out Ki and Kd and increase Kp until we see sustained oscillations in the output. So what that means is with a value of Kp equals 50, Ki Kd equals 0, we can see what type of a response we get. And this is the closed loop step response that we get. We're not paying attention to whether it's tracking or not or the speed of the response. We're simply looking for that sustained oscillation, which so far we don't have. Okay, so we're going to need to increase Kp. We'll bump that up maybe by a factor of 2, bump up Kp to 100. And just rerun the same simulation until we see the closed loop step response. Now I'm seeing more oscillations as to be expected, which is what we discussed before. We should expect to see more oscillations and a faster response by increasing Kp. But again, all we're looking for is sustained oscillations, so 100 was not enough. Let's go to 150. So what I mean by, I mentioned that, you play around with the control knobs. This is what I mean. You're cranking up that gain, Kp, and you're going to see the effect on the closed loop response. Okay, so now we have more oscillations still, but I still wouldn't consider this to be sustained oscillations. Let's try 200. At a value of 200, oh no. At a value of 200, you can see that we're actually starting to go unstable. The response is actually growing, and if we let this keep running, it will actually diverge to infinity. So 200 was too high, which means we need to dial it back a little bit to say 190. Okay, at a value of 190, we're getting awfully close. We're seeing a lot of oscillations, but there's still a clear dissipation of energy. There's still a clear decay to this step response. So we can go a little bit higher, perhaps 193, maybe 192, and we'll just run this, and lo and behold, at a value of Kp equals 192, I fail to see any amount of decay or exponential growth in this response. So I would consider this sufficient for establishing sustained oscillations. So we've got our ultimate gain. Now what we have to do, remember, is to actually go into the data, right? Just zoom in, find any peak-to-peak time difference to get our ultimate period. So it looks like 12.2 roughly minus 10.9, something like 1.3 seconds or so. Okay, so ultimate period is roughly 1.3 seconds. Ultimate gain is 192. Okay, so presuming that we did our tuning method properly, we have our ultimate gain and our ultimate period. Let's look at this little cell here. Okay, so obviously I've done this before, but we've determined that for the ultimate sensitivity method that Ku is about 192, and based on that we got an ultimate period of 1.3 seconds. Based on these two values, we'd simply go ahead and plug into the equations that we wrote down earlier for the Ziegler-Nichols tuning methods. That's all this is just a direct application of these gains. So now our gains are going to change. And in fact, what I should show you is what the gains actually are. So I'll bring over the MATLAB window, and I'll just show you that once we apply those equations, the Kp that we're actually going to use in our control works out to 19.2. Ki is like 29.5, and Kd is about 3.12. So none of the gains are zero anymore. Okay. We have a fully populated PID controller, and now running the same exact simulation as before, but with a fully populated PID controller, this is what our response looks like. And it's just beautiful. This is a great response. Notice that we attempted to track a unit step reference, a value of 1, and our output, which is the blue line, goes exactly to 1. So we get perfect tracking, and that's of course because of the integral controller. But also our response time is incredibly fast. Okay, so we're going, our settling time is under 8 seconds, maybe 6 or 7 seconds, which is much faster than 250 seconds on the open loop response. And we get a little bit of overshoot, about 20% overshoot or so, which sometimes you just have to deal with, right? And this is a great starting point for a closed loop PID tuned response. Now, from here, remember that these gains are just a starting point, right? If you find that that's too much overshoot and you simply can't live with 20% overshoot, well, you have a theoretical understanding now of how the gains work, and you ought to be able to either reduce Kp a little bit or perhaps increase Kd to smooth out that response and get a little bit fewer oscillations and a smoother response. Increasing or decreasing Ki, well, as we saw, Ki serves to improve the steady state response, but if you increase Ki too much, you then tend to introduce more oscillations into the system. Okay, so I would say based on your theoretical knowledge, you either decrease Kp and or Ki, or you increase Kd to fine-tune this response. Okay. Now all we're going to do is basically we'll do the same procedure, okay, but we're going to use the quarter decay method. So this time we're not going to aim for sustained oscillations. What we want to do this time is to try and achieve this quarter decay phenomenon, where so the height of B over the height of A is about 1/4. In order to do this, the nice thing about setting up the code this way is I don't have to do anything else but start over and just start messing around with the gains. Okay, so again, I'm going to zero out the integral and derivative terms, start with a Kp of about 50, and with this cell, there's a little bit of extra code in it, and all that code does is to print what's called the quarter decay ratio. Okay, so the height of that little gap between the second peak and the green line, which is the final plot, to the first peak to the final value, that ratio is 0.105, which is not 0.25. We're looking for 0.25. So what that means is we ought to increase our Kp a little bit. Maybe we'll go to 70. So turn it up just a little bit. Now we increase Kp, and now we've got a quarter decay ratio of 0.218. So getting closer to 0.25, but we still need to go a little bit more. Okay, so in the interest of sparing you some time, I think you get the point here. We will go to a magical value of 75 and run this, and lo and behold, we get a quarter decay ratio of 0.248, which is as close to 0.25 as you need to be for tuning purposes. Okay. Now remember, this response itself isn't all that great, and we're not aiming to produce an awesome response right now. All we're trying to do is produce a quarter decay ratio, and so we've done so with a gain of 75. But remember, for the quarter decay tuning method, the ultimate gain is actually twice the KP that was used to produce that phenomenon. So the ultimate gain is actually 150. Okay. Now the ultimate period, again, we need to dig into the data and actually figure out what the peak-to-peak time is. So this looks like roughly 5.8 or so. And then we've got roughly 3.9. So maybe the ultimate period here is about, I don't know, 1.9 seconds. Roughly speaking, 1.9 seconds. Yeah, sure, we'll go with that. Okay, so ultimate gain of 150, ultimate period of roughly 1.9. And then, okay, yeah, so I've done this before as well. Okay, so the ultimate gain here was not 75, it was actually twice 75, so we'll call that 2 times KQ. Ultimate gain, ultimate period is 1.9, and then we plug into the same 3 equations that we did before to redefine our PID gains. Now with this updated set of gains, remember the gains are no longer 0 for Ki and Kd, they're all populated now. In fact, I can show you what they are now. So these were the set of gains for the ultimate sensitivity. For the quarter decay, Kp is actually 15, and Ki is actually 15.8, and Kd is actually 3.56. Okay, so with respect to the ultimate sensitivity, we have a smaller Kp and a smaller Ki and a slightly larger Kd. So if you think about what to expect with this response, we should expect actually a smoother response that's perhaps a little bit slower, but will definitely not overshoot as much because there's more effective damping in the system now. Nonetheless, we can just check it numerically. Okay, so at this point, we can actually just check to see what that response looks like with those updated set of gains. And as expected, we see a slightly different closed loop response, which is equally fantastic if you ask me. We're still tracking perfectly because of the integral control, but just like before, as opposed to before, we get much less overshoot, right? So this is 1.2 here, so this is probably about 6 or 7% overshoot, which is much better than the 20% we had last time. And we're not seeing a lot of oscillations either. Okay, so the only drawback here is that it takes a little bit longer to settle. But again, that's the game that you're playing. You're playing the game of, well, how smooth do I want it versus how fast do I want to get to my final value. Okay, so this has been an example of how to tune a PID controller using the Ziegler-Nichols, a couple of the Ziegler-Nichols tuning methods. And remember, right now we're on this path, this avenue of doing control design with an unknown plant. Okay, so this is the only departure in this course where we're going to do any type of control design with an unknown plant. And as soon as we jump back into topics like the Routh locus or the Nyquist design methods, you have to keep in mind we're going back into that avenue of control design with a known plant. Okay. Okay, so I hope this lecture was useful. This is, in my opinion, one of the more practical lectures because this is something that you can do starting today, right? If you don't want to spend the time to take a graduate course in system identification to determine the plant transfer functions, well, you have this, a PID control tuning that you can implement from day one. Okay, so I guess I'll leave you with that, and just know that next time when we jump in with Routh locus, we're kind of right back into this avenue of doing control design with a known plant. Okay, so we'll see you in that next video.